In this video, I'm going to prove what we called in class proposition 8.8.a. And this concerned the convergence of the so-called p integrals. So, what do we mean by a p integral? Well, if a is bigger than 0, then we refer to an integral of this type here, an improper integral of this type here, as a p integral. So it's an integral from a to infinity, where a is just some positive constant, of the integral 1 over x to the p. All right, so that's what we mean by a p integral. And what the proposition is saying is that this p integral converges if p is large enough, namely if p is bigger than 1, and it diverges otherwise. All right, well, you're not going to be responsible for this proof, and you won't need to recall this fact, but for this class, but nonetheless, it is good to be familiar with this proposition because it will be of some importance if you take intermediate calculus part 1 when you talk about convergent series. Okay, so for the proof, well, case 1, when p equals 1, well, I'm going to let you do that yourself as an exercise. In other words, in this case, you're supposed to show that the integral from a to infinity of 1 over x, this is going to look like 1 over x when p equals 1, this improper integral diverges. So that's what you want to show. Okay, so I'm going to now give the proof when p is not equal to 1. And it's not really a proof, it's just a question of computing this improper integral. Okay, so what are we trying to show? We're trying to show that this improper integral here converges when p is bigger than 1 and diverges when p is less than or equal to 1. So if you want to think about this integral here, this improper integral, as representing the area of the infinite region here beneath the graph of 1 over x to the p on the interval a to infinity, what we're saying is that if p is bigger than 1, then this region here is going to have finite area, and if p is less than or equal to 1, this region here is going to have infinite area. And that maybe makes sense, if you like, because as p gets larger, x to the p is going to go to infinity faster. So 1 over x to the p is going to travel to 0 faster. And so the area of this region in here, it can be expected to be smaller as p increases. All right, so what is this improper integral? Well, as always, by definition, this just means the limit as t tends to infinity of the integral from a to t of 1 over x to the p, which I'm going to write as x to the minus p, because we're going to integrate dx. All right, so what is this equal to? Well, this is equal to the limit as t tends to infinity, finding our antiderivative of x to the minus p. We'll just add 1 to our original exponent, and now multiply by the reciprocal of our new exponent. Looks like that. And evaluate at t and a and subtract. Now this is equal to, pull that 1 over minus p plus 1 out of the limit and write it as 1 over 1 minus p. And then the limit is t tends to infinity, evaluating at t, we'll have t to the 1 minus p minus a to the 1 minus p. All right, so what we see then is that our improper integral is going to converge if the limit as t tends to infinity of t to the 1 minus p exists as a finite number, and otherwise the improper integral is going to diverge. So all we have to do to check for convergence is evaluate the limit as t tends to infinity of t to the 1 minus p and see if it exists as a finite number. If so, the improper integral converges. Otherwise, the improper integral diverges. So we'll consider two cases here. The first being if p is less than 1. Well, if p is less than 1, then 1 minus p is going to be bigger than 0. And so, in this case, the limit as t tends to infinity of t to the 1 minus p, well, because 1 minus p, our exponent, is positive, as t gets big, t to the 1 minus p also gets big. And so the overall limit is going to be equal to infinity. So what does that mean? That means that if p is less than 1, this limit is infinity, and therefore the improper integral diverges. So let's just write that down. Okay, so hence, if p is less than 1, our improper integral, this p integral, diverges as claimed. Okay, so our next case is if p is bigger than 1. Well, if p is bigger than 1, then in this case, p minus 1 is bigger than 0. And so, looking at the limit that we care about, the limit as t tends to infinity of t to the 1 minus p, we could write that as the limit as t tends to infinity of t to the negative p minus 1. That's just minus p plus 1, which is what we had before. And now, this is equal to the limit as t tends to infinity. Let's write this as a positive exponent in the denominator. Well, what do we have? Well, as we said, in this case, p minus 1, our exponent here is positive. So again, as t tends to infinity, t to the p minus 1 is tending to infinity. So for all t's that we're considering here, we have 1 over a very, very large positive number, which is going to be a very, very small positive number. In other words, this overall limit here is going to equal 0. All right, so what do we have? We have that if p is bigger than 1, this limit here that we were concerned with is going to be 0, and going up, as before, what have we shown? We've shown that if p is bigger than 1, the limit as t tends to infinity of t to the 1 minus p is equal to 0. That means this overall limit here is going to exist as a finite number. That means that this improper integral here converges. All right, so what we've shown then is that if p is bigger than 1, the improper integral converges. I'll just write that down as the last statement right here. Hence, if p is bigger than 1, we've shown that our improper integral, a to infinity, 1 over x to the p, in other words, this p integral converges. That's it.